Welcome everyone. This is the call to discuss chip number 12, the plot filter reduction. And we have a few people joining us today on the call. And as well, we have myself. I am Dan Perry. I'm a technical writer here at Chia. And mostly JM's going to talk about this chip. And do you want to introduce yourself, JM?
Yep, this is John Michael Hands. I'm a VP of Storage.
All right, that was quick and easy.
Chia farm.
and a well-known Chia farmer. All right, so let's get going on this chip. I guess the first question that I wanted to ask you was, what is plot grinding? Can you explain that briefly?
Yeah, so we previously in the documentation we had something called a replotting attack, and if we get into the actual consensus, there's like a long range replotting attack and a short range, and there's some other stuff. And we thought, so one of these where the short range replotting is actually not really an attack. So we, Bram likes to call things that are grinding. So, when we sat down to kind of look at this, Bram and I just said, okay, let's just call it plot grinding. That's really what it is. So what you're trying to do in plot grinding is when you receive a challenge, or in the signage point, you're trying to create a plot that automatically passes the filter, right? Because at the time in the challenge, you can basically create a plot ID that automatically passes the filter. And then after the challenge is done, you can throw away the plot. And so the idea here is not to actually store the plot, but is to try to create the plot on the fly. This obviously is super challenging because you have to make a plot in a very, very short amount of time. In the past, we thought it was like about 3 signage points. It turns out there's some amount of space you can like spoof if you're under like 37 seconds, but it's like extremely small. And so one of the things we'll do today is kind of talk through the math about how this works. But okay, so now you're trying to create a plot on the fly, and once you get a challenge, so one, you have to buy the equipment to do this plotting, and you're not storing the plot, so you don't get the value of copying it over to storage media non-volatile memory after you create the plot, and it takes a certain amount of energy to create a plot. Right now with GPU plotting, we're somewhere in the neighborhood of like 0.1 to 0.2 kilowatt hours of energy consumed for a terabyte of plots. And so the math on this, and I think that's where we'll probably spend, where we made a model based on this replotting in plot grinding attack vector, basically to kind of simulate different scenarios for different plot times, different hardware, and different energy costs. The most important thing is there's no free lunch here. Like, the person that's trying to do this has to actually run a machine. It takes electricity, it takes equipment. So yeah, there is no free lunch here.
All right, and there's a lot. You threw out a lot there. So the next question, I guess, at what point will this become not necessarily economical, but just possible? Do you have a prediction?
Yeah, let me pop open these are just the same slides that I shared in the public blog post. Let's see if you guys can see this okay?
Yeah, I see it.
Okay. So yeah, I just described plot grinding, and really, you want plotting to be low amount of time, because that means you're creating a plot with less energy, and that's more efficient, and it's easier for the people that are farming. They don't have to spend a lot of time replotting to plot their space. So plotting fast is a good thing, and but this too fast is like, okay, once you have this total plot times under like 30 seconds, really it's this phase 1 under 30 seconds. Now you're into the territory where you're in this kind of danger zones where it's a little bit too fast. Okay, now the entire constants on the network, like K32, was chosen to specifically deter this. We at mainnet launch, it was kind of like right between K31 and 32, and at the time, Gene and Bill ended up making the decision for K32, but because they just did some at the time we had phase 1 parallelized in CPU, and we were kind of doing some math on memory bandwidth. And the idea for K32 was like, okay, let's just try to pick something that's going to be at least 5 years. The filter of constant of 512. I talked to Bram about kind of the history on that. It just seems like a reasonable, to them, it's saying, okay, let's just make the IO as low as possible to make this farming workload just like stupidly easy. Now that we have a lot of measured data on the farming workload over tens of exabytes over almost 2 years, we understand this plotting workload extremely well. 512 is a little bit overkill, right? You can go to 256 and the IO on the drive is still going to be 99.5% idle instead of 99.7% idle. So, but this combination, this 512 filter and K32 was kind of chosen as supposed to be the sweet spot for farming. So when we look into this future, and maybe I'll start here, which is just like, so to do this plot grinding, you don't have to actually make a full plot. So the plotting happens in different phases in BladeBit, and Mad Max, I think, is very similar, right? We have phase 1, which is the forward propagation. Phase 2 is some pruning, and phase 3 is this algorithmic compression that does line points and deltas that turns this couple 100 gigabyte clump of data into a final plot file. Now, when you're doing this plot grinding, you don't have to do phase 2 and phase 3. Like, it's just not required. So you can just do phase 1. And so for phase 1, we've kind of measured the exact amount of data you need to upload and download to complete a phase 1. Meaning this is the amount of memory that has to be transferred from like the GPU to the host memory to do this. So obviously GPU speed, this speed of which you can transfer data, is extremely important. That's PCI Express bandwidth. And so, so for one, PCIe like Gen 3 was around for like almost 10 years. So Gen 3 was kind of this weird, it was very stable. It took a long time to get Gen 3 working. I know, because I was at Intel when we first got it working, and we've all enjoyed PCI Gen 3 for a long time. Gen 4 actually came out in like, I think it's like spec was 2017, 2018, end of 2017. And it took a long time for Gen 4 devices. We didn't see Gen 4 in servers until Ice Lake on the Intel side, but in Rome on the AMD side. But it took a lot longer than Gen 3. And Gen 5 is going to be even harder, right? Because every time you increase these speeds, it makes the hardware more complex. It makes the hardware more expensive. But there's this huge pushing driving factor, which is there's AI, machine learning, GPUs, accelerators. There's just a ton of stuff driving the need for more IO bandwidth. And so the PCI SIG is continuing to improve the spec and making it faster. And system vendors are now, we just saw the announcement from Intel that the first workstation that supports PCIe Gen 5 is actually, with many, many lanes of PCIe Gen 5, like 112 lanes, I believe. Is actually launching in March, in 1 month. We have PCIe Gen 5 on consumer desktops now, from both AMD on the latest Zen 4 stuff from AMD, and on Intel for Raptor Lake. And so now we have a bunch of platforms for Gen 5, and now devices will follow, right? So now that we have the platforms, we'll see Gen 5, PCIe Gen 5. So PCIe Gen 5 is 128 gigabytes per second total bandwidth, so 64 gigabytes per second in each direction. And so in this plotting workload, you can transfer data and receive data at the same time. PCIe is full duplex; it can read and write at the same time. And so the theoretical time to complete this phase 1, if you have a GPU that's on the PCIe bus, is going to be limited by PCIe bandwidth. And we see this very directly, right? If you take a card today and make a full plot on PCIe Gen 3 and you move it to Gen 4, you're almost seeing a 2x improvement on speed if you have enough CUDA cores. There's some lower end cards that don't see that full 2x, but we're seeing 2x on like even cards like a 3070 or something like that. Like, so this is not a tremendously expensive card. It's like a $400 card. So this math, you can use that same math and say, okay, if PCIe bandwidth is perfectly efficient and plotting is perfectly efficient, and you have infinite CUDA cores, infinite compute, the plotting time would be actually limited to about 20 seconds of total downloads and 15 seconds of uploads, assuming you could get perfect bidirectional bandwidth. on PCIe Gen 4. Now, in practice, we see about 26 seconds. So Harold and we have actually done this test for a phase 1. And yeah, we're able to get a Gen 4, PCIe Gen 4 phase 1 with infinite compute, meaning like a high enough card to saturate the compute of Gen 4 down to 26 seconds. So the real problem with block grinding is we don't want, if there'll always be compute. There's AI clusters, there's AI training machines that have like tens of GPUs. Like there's always going to be like these massive, insane systems that are just going to shred plots to bit. But you have to make it so those are like, to running one of these to make a plot would be just so unreasonably stupid and expensive that you wouldn't want to. It costs more energy to keep it on than it is to create plots. But the problem with plot grinding is when you can start doing this on a single card, because then now people can look at doing this on like a desktop. Even with dual cards, people can buy a workstation or something like that. Now PCIe Gen 4 workstations are going to be the N-1 platforms. People will be able to get these pretty easily. So this plot grinding becomes a problem when people can make a plot and make this phase 1 under 30 seconds on a commodity machine. It's really not a problem per se if they can do it on like a stupidly high-end machine, because that's always going to be possible and it always will be possible.
Great. Yeah. Thanks for the explanation there. And sounds like coming down the pipeline, once PCIe Gen 5 comes out, then we'll really start hitting that problem where commodity hardware could potentially really start hitting these fast times. So we have a few mitigations against this, right? Against plot grinding. So could you go over what those are and what they would end up doing?
Yeah. Let's see. In that blog post on the plotting, we wanted to talk about GPU stuff in that blog post, all the awesome engineering we've done on the GPU, but we actually talked mostly about plot grinding. And in that blog post, we had this little table, and so Bram and I. Now the good thing is that I went through this with other folks at Chia, and we went through this whole thought process of like, okay, what are all the things that we care about? These are all the, we'll just say attributes and rationale. And then what are all the possible things in Chia that we have knobs to tune and we can change? And when I did this, I came to the conclusion of the filter. Bram wanted to start from scratch and just said, let's throw out whatever you have. Let's just start from scratch. We made a table and we went through, this economic plot grinding is basically like, okay, what can we do to make plot grinding less profitable? Well, if you reduce the filter, then you effectively are proportionally reducing the profitability of economic plot grinding by the proportion that you reduce the filter. So, right, if you reduce the filter by 2x, going from 512 to 256, you've now effectively halved the profitability of plot grinding. So that's proportional. Now, if we increase the K, this is also proportional, right? So we can move K32 to K33. And it makes plot grinding less profitable because now it takes longer to create the minimum size on the network. Today is K32. If we made it K33, then it would take this plot grinding a little bit longer. But it's not exactly one-to-one proportional. It's not like linear proportional like filter. It's a little fuzzier because you're going to hit different system bottlenecks as I described, like whether it be PCIe or memory bandwidth or whatever. So it's not as proportional as we would like. And then, Bram, we came up with other ideas about like, and these are in the chip as well, which are, which basically we kind of go through option to increase the K size all the way down to change the proof of space format, which is, we basically just said, should we just there more plotting tables? Bram had this idea for this plot grouping, like maybe you could make K32s come in pairs. And we went down those. So we're going to probably spend most of the time talking about these two, right? The K and the filter, because these are the most effective way. You increase the tables or changing the proof of space, it would be effective, but as you get down to here, it's not only a hard fork, but it's a complete replot for everybody. So that's a tough one to swallow for everybody. So this 51% attack plot grinding is, it's something we do care about, right? Which is if somebody can do plot grinding now, instead of just having to buy storage and plot it to try to perform a 51% attack, which today they'd have to buy whatever 24 exabytes of storage, which a couple $100 million, right now, security, and that was not, not very easy to obtain, but we don't want somebody to be able to just rent GPUs in the cloud and then all of a sudden spoof up tens of exabytes of storage, right? So this 51% clock grinding, well, turns out then, these same methods for filter and K, produce that, make that more expensive by a factor of whatever the clock grinding, whatever the filter and K value is. So, right, it's just very similar to clock grinding. So the honest plotting is just for farmers that want to actually plot their storage and then transfer it to non-volatile memory, like their hard drive. The filter reduction has no effect on it. Like changing the filter does nothing for people that are plotting it. So that's good, but for increasing K, this is huge, right? So if people are already feeling the pain of plotting K32, and we finally have made it easy enough where, 2 years into mainnet, where it's not terribly hard. There's a lot more tools today to do plotting. But if you go to K33, now you basically have to double the memory requirements to do this completely in memory and no disk writes. You double the amount of disk writes to create a plot. You double the amount of resources required. It's just a lot harder to create a K33 than it is to create a K32. So the amount of hardware that people have to buy to plot goes up by a proportional factor when you increase the K value. And then when you increase the K value, now you're invalidating all the K32s that are already in the network. That's about 24 exabytes of K32s. And so, this required replotting is, went up, and now the filter, again, it doesn't change anything about plotting and honest plotting. So it just changes the filter. Where the filter does change is during the harvesting. And this is as we describe in the chip, the biggest effect of the filter is the entire point of the plot filter is to reduce the IO to disk by a factor of 512. Well, the filter is really good at its job because it reduces the IO to the disk. Now the disk is 99.7% idle. So now when you half the filter, it doubles the amount of IO to the disk and doubles the amount of decompression you have to do. But one, this affects everybody equally. So it's not like somebody has a competitive advantage here. And two, it still leaves the drive extremely idle. The drive is still going to be 99.5% idle at a filter of 256. And so when we looked at this, the best benefit of this in the honest harvesting is, yes, there's a hit here, but it's not terrible and it hits everybody equally. Whereas increasing the K doesn't change harvesting really whatsoever, right? I mean, because you're increasing the minimum K value for everybody, there's not some advantage for anybody with K33s. And then, we said here custom plotting advantage. If you go to K33, then now people that have more money and more higher value systems have a competitive advantage over the little guys, even more so. With the filter reduction, there's some custom harvesting advantage, right? If you have GPUs, you get a little bit more efficient decompression for harvesting. But really, it came down to this. These are the two options we looked at, and it came down to hard forks are something we didn't really want to do, but everything else checks the boxes here. That's pretty good for the filter reduction, whereas every other thing we looked at required 100% of the net space to replot. And this is what it ended up boiling down to, which was just like, do we make everybody replot all their space? And we've seen now there are some open source tools, and we're making our Blabit, CUDA, and all our plot compression open source. There's some closed source tools that allow this plot compression today. And if those were successful and a lot of people were replotting, we would expect to see a net space increase because the effective capacity of the net space, there's more effective capacity out there. We'd expect the net space to increase, that these things like GigaHorse from Mad Max and other stuff are available. And we haven't seen that. Like maybe one, went from 20 X EIB to 21 EIB.
Yeah, that's a good point. I hadn't really thought of that.
I just don't think that many people are going to replot. I don't think that 50% of people are going to replot. I don't even think that 20% of people are going to replot because it's hard. And a lot of people have their Chia system set up and just don't care. And they're just going to leave it running because they already set it up and they're making some revenue and farming rewards. So we didn't want to hurt those people by saying, okay, now everybody has to replot. And the filter was, for us, a compromise, for Bram and I, when we looked at this criteria, it was like, okay, well, this seems reasonable. It checks all the boxes. It's a constant that we quite literally have set to that we know exactly what the effect of it is. We know when we reduce it that it increases the IO to the disk and it increases the amount of decompression we'll have to do for plot compression, and we know exactly what happens to plot grinding. It will decrease the profitability of plot grinding by a factor of 2, just nice and clean, no tricks, no weird funny things. It's just extremely straightforward.
Yeah, great, thanks. So it sounds like you said, this ticks all the right boxes, and there's very little disadvantage to doing the filter reduction, except there is one, and that's that it's a hard fork. So could you briefly explain why this would be a hard fork and not a soft fork?
Yeah. So in basically, if you we're not we're loosening the rules here, or we're saying that before, if a plot passed the filter of 512, it would have been valid. Now we're saying in the new consensus, it would say, okay, if you had a plot that filter that passed the 512, now that is invalid. So we're taking something that used to be valid in the old consensus and making it invalid in the new consensus, and that is something called a hard fork.
Oh,
if we had,
I think you said that backwards.
Did I say that? Wait. Oh God,
we're
now you're confusing me. Okay, so we had something that was valid in the old. No, it was valid in old consensus, not valid in new consensus.
That's what it would be with the K increase, right? Because
no, it wasn't. Sorry, yeah, I was gonna say we're taking something that was valid and making it invalid. Yeah.
No, because you have, sorry to correct you, you have previously or currently, if let's say you have 512 plots, one of them is going to pass the filter, right? And all the rest will not. After we reduce the filter, now 2 will pass the filter. So you're going to take something that was invalid before that this plot passed the filter and then make it valid.
Oh, yeah.
Right. So you're opening the rules a little bit. Yeah, no big deal.
Drinking some coffee here.
It's kind of mind bending
to
think about it, but that's the reason why.
Yes. So yes.
Right. So it'd be a hard fork.
Right. And the soft fork, for the K32, for K33 is because K33s are already allowed on the network.
Right.
So we're not taking something that was previously invalid and making it valid.
Right. If you have a K33 now, and then we increase the minimum size to K33, it remains valid, but 32 would drop off. So that's kind of the one advantage of doing the K increase, but it seems like it's far outweighed by all of the disadvantages.
Yeah. So the only thing that's not great about the hard fork, is that it just maybe requires longer than a soft fork to activate, because you have to get the majority of farmers to agree that this is a good thing. I tend to think that farmers would be like, yeah, we don't like plot grinding. This is not something that we want on our network. I'll support this. At least that's what I've heard from farmers. That's what I assume farmers will say. But you guys are here, right?
Yeah, I mean, ultimately, this is a chip, so it's a proposal, and it can be accepted or rejected. And if we don't do the plot grinding, it sounds like the only other real option that we have is increasing K, which has all those other disadvantages. So what would the timeline look like on this then? As far as, I guess, there'd be 2 phases, right? We'd have to put this in a build, and then the second phase would be actually activating the fork. We don't need specific dates yet, but it's still too early to say the dates. But
yeah, the good news is this is like this 256 filter is not a very much code. It's just mostly testing, because these are just constants that we have set up in the blockchain. So the way that we set it up in the chip is that the filter would reduce over time, and this is the only thing we have to go make sure to test. So the reason we did this, instead of just saying, okay, now the filter's 56 and go along our merry way, is we don't want to have to hard fork again. So the idea is just, okay, we'll just do one of these, and then I think in the chip we said every 2 years. I'll talk about another chip that we opened that I think we'll maybe make that a reduction on a 3-year cadence more feasible. So yeah, and we can, I don't know, Dan, if we have time today, we'll talk about the other one we opened.
I think we can mention it briefly that we do have a second chip, but it is a somewhat separate thing. It's just a neat little trick that someone at Chia figured out. So I guess the next big question I had was, why did you choose 4 times to reduce the filter specifically and not like more or less?
Yeah, so we know the farming workload today, which is about 0.5 IOPS on a 18 terabyte drive. That workload goes up as you get higher capacity drives because now you have more plots on the drive, and there's slightly more plots that pass the filter on each drive, and it's obviously there's some sensitivity on pool difficulty and some other stuff, size of farm and stuff, but in general we know the farming workload's about half an IOP, and so a hard drive can do about 200 random read IOPS. So hard drives aren't getting faster. I mean, there's dual actuator hard drives, which kind of like are faster. There's just like 2 hard drives in one, right? You have actually two actuator heads that, but they're higher power. These aren't really for Chia type workloads. These are like for like hyperscale warm storage workloads. Like think about like meta blob storage for photos and videos and stuff like that. So hard drives aren't really getting faster, and we know what a hard drive can do. So we know how far we can push the filter before hard drives break. And so that's kind of where the filter 32 still won't break hard drives. I think we'll still have some room where it's like still decently, I think when I calculated it out, it was still like 90% idle or something, because we don't want the drive to be like super busy and taking a bunch of power either. So filter 32 was enough to get us to whatever 8 years from now. And maybe if we do a 3-year cadence on the halvening of the filter, it's like much longer than that. And so somebody made a comment on the chip that was like trolling me. Spaceport was just poking at me, just laughing, because I said, you can't predict technology out past 5 years. You can 5 to 7 years is like the time where, okay, well, we know hard drives can be still used for archive storage. We know what it would be highly unlikely that Seagate WD go out of business in 5 years from now. So we know what hard drives can do, and so 32 is still reasonable. Like, where hard drive farming is still reasonable. Now, if you go past 5 years out, then there's a lot of interesting scenarios where maybe SSDs, with higher capacity and lower TCO, then hard drives become reasonable for farming. Maybe people start making them with used NAND. There's a ton of different scenarios, and so you don't want to like totally block any of these scenarios out for what happens for farming. At the end of the day, farming's just a market thing, right? People are going to farm on whatever's profitable and whatever's cheapest, lowest total TCO. So we don't want to make the filter so low that hard drives don't stop working. Now, if somebody wanted to, fork Chia and make a new constants that was SSD only or low filter and plot grinding only, they can do all this weird stuff. Like, we're not going to do that in Chia. We're going to keep hard drives around. So
sounds good. So we're planning out for several years in advance, but not forever, and see where the future takes us. So that was all the questions that I personally had, but a few have come up in the chat. I'm not sure if these will show up on the recording, and maybe we should just go through those. And if you guys want to ask additional questions, how about you? If
you could certainly unmute and raise your hand.
Yeah, let's do raise your hand, and then I'll call on you.
Call you.
Let's start with Johnny. Just raise his hand. Johnny, can you just say your question?
Hey, John.
Yeah. So just as a point of clarification, when you did your CapEx and OpEx calculations for the economics of plot grinding, was that with the 3x multiplier that CHIP-13 is going to address? Like, are we expecting CHIP-13 to be implemented as well with this?
Yeah, maybe that's a good way to, maybe that's a good segue to just flashing up this thing.
This is that neat little trick that I mentioned.
Yeah, I'll show you. So I shared this. Let me to share here in the chat. I think this is linked in the post, but this is the model, right? So the equations kind of get tricky, but if you have a phase one time between 28 and 37 seconds, the leverage equation is just 37.5 minus the t time to plot divided by t times the filter. And then if you're between 18.75 seconds and 28 seconds, now you're 9.375 seconds. That's the time of a signage point divided by t times plot times filter. This is where it starts getting scary, right? Is if you have a plot time between 9.375 and 18.75 seconds, now you can generate a plot ID that passes multiple filters and multiple challenges, and you can start spoofing more space by a leverage of 2. And if you get under 9.375 seconds, now you have an additional 3.5 leverage, because you can make a plot that passes multiple filters at once. And so this tab called plot grinding today, you can just pop in the constants today, like so you can pop in whatever $43 for Chia or 21 next EIB of net space, whatever it is today. And you can see today plot grinding's not really profitable for anything. Maybe if you can make a plot in 2 seconds, you can be profitable. And again, this is just my made up costs. For here, I just said, okay, we're gonna draw the line at like 1 GPU or 2 GPU kind of systems, and we'll just say 10 cents kilowatt hour. But I played around with these models. The problem is not when it's kind of hard to explain. It's the first derivative of the price. So if you go if the price goes to say $100, now all of a sudden it makes some of these plot grinding scenarios profitable. Now, if the price goes to $100 today, that's a big enough increase in farming profitability that honest farmers will actually plot space on the network, and it will increase the net space and it will reduce that profitability back. And so the rate of change of net space is tied to the first derivative of the price. So if the price goes up really fast, then the net space will go up because people are now farming super profitable and people will go out and buy storage to farm. Now, the problem with plot grinding is that if the buttons are too easy to turn on, right? If you can just turn on plot grinding instantly, when you see these massive price spikes in Chia, we don't want a bunch of spoofed net space to come online because of plot grinding. So you have to have the order of magnitude difference of you want plot grinding to not be profitable. You want when you see these 2x or 3x spikes in prices, because it's crypto. We're probably going to see some weird 2x, 3x prices. So the thing in was it chip 13, Dan?
Right, 13
is the other one. So we found a cool trick that says basically, if you can disqualify a plot that has passed, or if a plot passes the filter, it's now disqualified for the next 3 challenges. And the honest in the real world, the probability of this happening is not very good, right? You take, if your plot passes the filter, that's 1 in 512. The probability that passes another filter in a row is 512 times 512. The probability of it passing 3 filters in a row is 512 times 512 times 512. But this is really big. We just talked about it. It's a really big advantage for the people that are grinding, because they can basically make this plot that passes multiple filters. But in the real world, it just doesn't happen very often. So we had this cool Quexington from Chia, Matt, came up with this idea, which said, okay, well, why don't you just disqualify a plot from passing multiple challenges in a row, and that kind of shuts down this leverage. And so that's that third tab, that plot grinding consecutive filters. And then we have another scenario where we add that and the filter of 256 into this. And you can play with the model. Again, it's a model. It's not just a static model, which is what the price today is and the net space is today. You can play with the model and say, what happens if the price 5x's or 10x's? And you want it to be where if the price 5x's, that plot grinding is still not profitable. Because if the price 5x's, for a fact that the net space is going to grow from honest farmers. So this is that balance where we want to be, where we want to make it so it's if the price goes up, the net space comes online from honest farmers. And all that's in the model.
Right, that makes sense. And net space is probably going to catch up a lot faster now with faster plotting.
For sure. Yeah.
So because there is a sensitivity to the price, somebody else had this comment in the PR. Is the timeline informed at all by the halving cycles of the rewards?
Yeah, and that was to where Dan was at. When do we want to do this thing? I think, after everything I just described, hopefully everybody's on the same page of like, this sounds like a reasonable thing to do. It seems like we should, it seems like farmers would be for it. It's like shutting down block grinding. No farmers want like GPUs to spoof a bunch of space and, make 10 or 20% of the network proof of work. That would suck. So I think doing this before the halvening would be reasonable. I don't know what the hell is going to happen with price at the halvening, but a reasonable person would say, okay, if you keep demand the same and you half the supply, then what's going to happen? If there's more demand than supply, then the price will go up. And so I think in the very first halvening, it's reasonable to expect that we'll see something interesting happening with the price. I don't know what's going to happen, but I think we should prepare for that, right? And try to get this thing done before then. So we have a year from now, right? It's a year, 13 months or whatever from now.
Yeah,
roughly.
approximately a year.
Yeah. So yeah, I think it's reasonable to try to get this done before then, so that now that second chip, that chip 13, which is the consecutive filters, that could be done as a soft fork, and that could be done earlier, which effectively shuts down a lot of the leverage. But if there's not a bunch of people, if there's no bad reasons to do the hard fork, and again, something that Dan's working on is like, if we're going to do a hard fork, let's make sure we like only do one and make sure we have everything on the wish list in that hard fork, which is beyond the scope of this chip call today. But reasonable, if we get that done by the second half of the year and we have like a 1 year activation, that would work. I'm not great with these timings. I would say, my gut tells me 6 months is enough, but you don't want to jeopardize like any chain splits or any bad, it's just like the risk is too high to on some of this stuff. So I don't know.
Right. We're going to hammer out these timelines soon,
Yeah.
soon TM. And we'll definitely have a better view of exactly the block heights at which we want to fork. The downside to doing it too early would be anyone who hasn't upgraded to the version of Chia with this fork built in, they'll just drop off. So, and that's where you could get actually chain splits too if there's a significant number of nodes that are still on at that time that haven't upgraded. So we need to give people plenty of time to upgrade. So this is not like the kind of thing that we're just going to quick put in and
sneak it in. Yeah.
No.
Yeah, and and Chia said, like we said, hey, we don't want to do hard forks. And hopefully, just in the beginning, we described like, this is the case where the upsides are more than the downside.
Right. So if nobody else has questions, there were a few others in the chat. Maybe I could just quick read through those. If you do have a question, just raise your hand and I'll call on you. So this first question, I'm just kind of reading on the fly. Can I think of it right now as they would have to create a plot on the fly to try to hit the block currently, but then after the reduction, they'd have to create 2 plots on the fly to have the same chance of hitting the block? I'm not quite sure.
Yeah, so the way the filter works is the filter disqualifies a certain amount of plots at every challenge, right? So if there was no filter at all, every single challenge, you'd have to do a proof quality check on every single plot you have. So that would be a lot of IO, right, to the drive. Like even with a hard drive today, a modern hard drive that has 18 terabyte hard drive has like 165 plots, like that would be bad. So the filter basically just reduces the amount of plots that are eligible each signage point. So if you're an attacker or plot grinder, you can just always make one that passes that filter. And so yeah.
But if I could jump in, you can quite easily brute force the ID of a plot, and because you only have to guess on average 512 times before you get one that will pass the filter. So that's almost instantaneous. And so that's why you can always get one that passes the filter. And any plots that you have that pass the filter need to go through this quality check, like Jam said, and that's going to require 5 to 7 disk seeks, which is very little time for a single plot on a single disk. But if every single plot on your entire disk, I don't know how many an 18 terabyte hard drive has, but a couple hundred, I guess. if they all have to be checked, then that's going to take just too long for Chia to even work. So that's why.
Quick one, Dan. Are there some people that waiting to be let in at all?
I guess there's a couple left.
Okay, cool. Let's
There.
John. Yeah, John has a question again.
Yeah, I have a question around how this would impact compressed farming. So I'm going a lot off of the GigaHorse guidance right now because I think that's the most well documented. But you know, if we had like a certain CPU that's able to handle a certain level of compression, there's a maximum farm size that it could effectively farm, and the plot filter reduction would be cutting that farm size in half, right?
Yeah, exactly. Now, yeah. So what John was mentioning is, you know, if there was no compressed plots, then a filter change would, like, nobody would even notice. Like you wouldn't even notice it on the drives. Like it's the amount of, you know, doubling the IO from something from 10 kilobytes a second to 20 kilobytes a second is like nothing. But now, with all of a sudden, now we have plot compression. When you have a plot that passes the filter, you have to do a decompression event on that, and which is basically just trying to brute force look up some of the missing entries, and this takes compute. And so the way that we're going to have this in our farming simulator as well for compressed plots, which is for a given CPU and filter and number of and farm size, how many plots, how much storage space can that CPU support? So when you half the filter, you effectively half that number of it's like a straight 1-to-1, like just whatever the number, right? If he says at C7, a 3060 Ti can support 3.5 petabytes. Okay, well, now it's literally half that amount, like on the new filter. It's like exactly. So I thought about this in the beginning. I was like, shit, this is going to increase the power for a bunch of farmers, right? But this affects everybody equally. So it just moves the ball on, if everybody was going to use C7, now they have to use C6 or one level down. It's not going to actually make people consume more energy, because they were going to consume more energy as well already. It's just, they were already going to do the most profitable thing for their farm. This is game theory, right? They're going to optimize for their own farming selfish rewards. And so if you change the filter to 256 and it hits everybody equally, it's just going to make everybody have to think one step out, right? Which is, if I'm replotting today for compressed plots and I'm using C7, for instance, in a year from now, I either have to put a GPU that has twice the amount of CUDA cores in there to my farmer to do the decompression, or I'm going to have to replot to C6 for the same GPU. And so it does add some more complexity and we'll just say strategy to farming. Before, where it was just like, okay, you know, plot as fast as you can, that's farming. You buy the storage as cheap as you can, farming. Now there's tricks, right? Where if you have compute local to the farming node, you get a leverage factor by the amount of compressions. You get more rewards by having this compute local to the farming node. And so with the filter change, it just changes that equation by exactly proportional to the filter.
Yeah, that makes sense. I think my concern is like how aggressive the filter changes all the way down to 32. You know, you'd be cutting. I don't know if folks are going to think that, you know, my effective farm size is going to be reduced by 16, you know, in however number of years. But I think this also goes to one of the questions in the chat, which is, you know, it's an aggressive filter, but if we choose to relax it in the future, that's not a hard fork, right? That's a soft fork.
Exactly. So yeah, if it ever gets too crazy, we can soft fork it out, you know, which is why we started with 2 years. If we're able to do this, at least if you look into my model, it suggests that if we can do this other trick with the consecutive signage points and a filter reduction, that maybe we're okay with a 3-year cadence. And the 3-year cadence is not just made up. The PCI SIG is on a goal and historical bandwidth doubling every 3 years. And as you flashed up that computer, sorry, you can see it. I flashed up this thing, which is just like, I just graphed the, I think this is a Geekbench performance, whatever, you know, a 1080 versus a 2080 versus 3080 versus 4080, you know, and it was a 25% annual CAGR and 25% every year. So, you know, what that ends up being is, you know, between, you know, 2016 and 2022, you effectively 6x'd the, whatever, 6x performance, right? 50,000 to 300,000. Yeah, so we know that, GPU compute for performance is increasing, and I do not expect that to go down because of AI. AI is actually doing the opposite, right? I just looked at the GPU market stuff last night. I think it's like $15 billion a year for desktop and dedicated GPU cards, right? NVIDIA has 93% market share, like they're just dominating, right? So I don't expect this to slow down at all, right? PCI bandwidth is going up, GPU performance is going up. We probably want to be a little bit on the conservative side just because we're playing catch up, right? Like if the option of do nothing is actually pretty bad, right? Somebody in, PCIe Gen 5 GPUs are coming out on the data center side. Thankfully, these are like $15,000 from H100 or whatever. It's like, they're not going to be cheap. But in 3 years from now, we expect those to be like reasonably cheap, right? So, we never want to be in a scenario where somebody can take a single card and put it in a system and try to do this grinding. Because of the DRAM required for K32, we're probably safe to workstations where this is never going to be able to be easily done on a desktop. But yeah, it doesn't make me feel warm and fuzzy when somebody can take a workstation, pop in 2 GPUs and try to do this. That's something we want to shut down.
Great, thanks, Jam. And thanks, John, for reading that question too. Next question, I kind of glossed over this answer already, but maybe we could go into more detail, is what happens if you don't upgrade? Can you just keep farming and the plot filter, the previous plot filter will just work?
Yeah, so this is what happens in a hard fork is if there is a majority, right? The majority of the nodes are upgraded to the latest consensus, then they will start rejecting blocks from the old nodes because they have a new consensus and they're all on the same, they're all using the same version. And again, in Chia, we're Nakamoto consensus, you farm the longest chain. And if the longest chain is the one that has the new consensus and you're on the old consensus, then you're going to be bummed out when you try to submit a block for a filter of 512 and they say, well, that's not valid. Sorry, rejection. Because this is one of the things that, the full nodes will do when they're including a block is look at, you're validating the consensus, right? You have to validate that the farmer that made the block is following the rules. And if there's new rules, then you're out.
Aren't the plots that pass the 512 filter by definition also pass the 256 filter?
Yeah, that part's true, yeah.
Yeah, so if you're still in the old client, wouldn't you just have like half the chance of winning a block, but it would still technically work? You're still submitting valid proofs, right?
This might be true. I haven't thought about that enough.
Oh, right. You're just winning half the rewards. Yeah.
Yeah,
I
you're
guess
just hurting yourself.
You might be on the wrong.
would,
You might be on the wrong chain at that point, though.
yeah.
yeah, because you would see blocks that you would think are invalid, right?
Oh, right. Yeah, because you're seeing blocks that you're rejecting blocks that are valid, and so you would easily get this. You would easily get not synced from the blockchain, right? Because if you're rejecting blocks, if the full node is rejecting blocks that are following this new rule, right, then it probably wouldn't stay synced or something.
Yeah, you might be building off the wrong chain at that point because you'd be more lenient on blocks, and so you wouldn't follow the main chain.
Thankfully, we have Bill and Chris on the call too.
Which is another reason we need to make sure we have plenty of time for everybody to upgrade, because if a significant number of nodes are not upgraded, then they could start forming their own chain, which could potentially compete against the main chain.
Yeah. So yeah, we definitely want people to upgrade. That's pretty obvious, but yeah.
Yeah.
It's one of the risks. This is one of the risks of the hard fork, though, right? I mean, I guess the soft fork, there's also a risk of chain split, but it's not like catastrophic, I guess.
Right, and we can do those on a slightly shorter window too, just because of that reason. So it looks like we've answered all of the questions from the chat. If anybody else has questions, please raise your hand now. And otherwise, what's the next step here? I guess I would like to ask people if you have any opinion on this, for or against or whatever, just please weigh in. And the way you should do that is in the PR itself in the CHIPS repo. And we will be posting this on YouTube, so you can watch it again later if you missed something. This is something where we need buy-in from this. This isn't automatically going to happen, and hopefully we have given a solution that most people will agree with. But we'd like to know if you disagree somehow. Looks. Oh, we're getting one more. We're getting a couple more statements in the chat now. But they're not really questions. They're just
Yeah.
they're just opinions about what's.
If anybody else wants to, I mean, just general, John. Yeah, just like
yeah.
what do you guys think about this? Is
whatever you're writing in the chat, it's fine. But it's going to disappear. So it's better to put this in your opinions in the PR for if you're for or against this, so that they'll be permanent. Okay, John, your hand is up. Go ahead.
I'll ask one more question. So I agree K33 doesn't seem like a good move because that's effectively the same as cutting the plot filter in half for the purposes of the plot grinding attack. And the K33 would likely also come with a plot filter reduction plan, right?
yeah, there was, I guess I didn't go through that like option was like a hybrid option, right? We thought about one hybrid option, which is just like change the filter and then like maybe 3 years later, change the K and then change the filter. And it comes with a lot of the same thrash as just changing the K, right? And so we heard from folks like, well, really, like just please make K32 work until it absolutely does not, right? Until there's like, some people were making comments on the GitHub like, oh, can somebody put this sorting in an ASIC? Like, they absolutely can, but it's not going to be faster than GPU because you're not bound by the ASIC. We're not bound by GPU cores. We're bound by PCIe bandwidth and memory bandwidth. We're not going to. So you have a memory problem, not a compute problem at some point, right? So you can't just make an ASIC that's like 20 times faster for plotting, right? Because you can't just invent DDR that's 20 times faster, whatever. So
I think that's really helpful context, JM. Do you think you can publish some guidance on like under what scenario we would move to a K33?
Yeah, I'm these new the new GPUs from NVIDIA for training specifically. Now we've done some we'll say I've heard like if you just take the concept that I described, which is like, okay, if you're limited not by compute, generally limited by PCIe bandwidth, then you would say, okay, well, if you can fit all of this in GPU VRAM, then you can make a really hell of a fast plot. So today that requires like 4 A100s, A100 80 gigabytes. So I think you need 4. I don't think you can do it on 3. So, okay, these cards, even when the H100 all come out, I think the A100s are still going to go for, I mean, they're going on eBay for $12,000. I think the cloud guys buy them for $3,000 or $4,000. But these are real fast, right? These are like, if you have this whole thing in GPU VRAM, it could be like a 3-second plot. And so if you double that DRAM bandwidth for high memory bandwidth and you double the compute power, and you have like 8 of these cards, I mean, that scares me a little bit. Thankfully, these are all being used for AI and they're extremely expensive. Like these kind of cards, you cannot get these in a desktop card. You can't get them in a workstation card. These are like 700 watts soldered onto the freaking GPU board things, yeah, like, so we'll just say the AI training servers look a lot like something that would rip through plots in record time. Because they're optimizing for the same thing as plotting requires, which is compute and memory bandwidth.
Yeah, so we'll have to get some better guidance out there for you guys soon. And this chip is going to be open for a while, so there will be time to make small adjustments to it or finagle it a little bit. John also asked, how do we measure buy-in? And well, there's really 2 ways. Ultimately, it's do you upgrade or do you not upgrade, and that's up to you. But that's after the chip goes into effect. Before the chip goes into effect, really all we have is what you're saying publicly. So there's really 3 spots where you can leave comments where we'll definitely see them. One is in the PR itself. One is on developers.chia.net. That's a common place for people to chat about this kind of thing. And then finally on Keybase. And then obviously there's some other third-party websites that may or may not get traction if you post there. So there's plenty of spots that you can make your voice be known. And we're going to gauge community approval based on what we see out there. But this hopefully is a plan that will work for most.
And hopefully, by the time we have the, fork software done, not like the activate, right? The activation will be in a future block or whatever, but, hopefully we'll put it in a really nice release that has all kinds of good stuff like block compression and good stuff that you want to upgrade, and people will want to upgrade their nodes. So, we don't want there to be, it definitely makes me sad, right? When these hard forks, right? There's going to be 80% of people that upgrade and 20% of people that are just off the grid, not following Chia, and their nodes just go away. That sucks. But, we'll all do our part as community and farmers to help people upgrade and, get on and make them realize this is a smart thing. Again, John, others else, play with the model, play with the math. It's harder to visualize these, people want like a 1 number answer, and you have to tell, like I have explained this to other people, this is the same way SSD endurance works. People are like, what's the TBW? I'm like, it's not, it's a complex model. There's garbage collection going on. There's, there's NAND program race cycles, there's over provisioning, and there's all the workload. There's all this stuff that matters. It's not just a 1 answer, like 1 number thing, right? This is the same thing with block grinding. Like, it's just going to be, there's a ton of variables like price and, cost of power, cost of compute, all this stuff. So you just play with the model. And if you guys find anything interesting that I missed, I would love to hear about it.
All right. Well, thank you, Jam. Thanks for doing this, and thanks everybody for coming. And I'm going to stop the recording now, and we will